Hello everyone and welcome to a new course which is digital elevation models and applications. If you recall that earlier I have done 2-3 courses first on the GIS, then digital image processing and remote sensing also. So those who are having background of these subjects will definitely enjoy learning more details about the digital elevation model. Though digital elevation model has been briefly introduced during the introduction to or principles to GIS course, but now as you will realize that it is really a storehouse of information which we can derive from digital elevation model. So in this particular course we will be discussing about what is the basic concept of digital elevation model and how it is represented, how we can utilize it, which are the processes which we can perform on it, what are the products we can generate, and also various applications, especially in the field of civil engineering, earth sciences, and in other domain as well. So we start with this concept that a digital elevation model is basically if you recall raster data. So it's a raster data, it's a two-dimensional matrix, and each cell of that matrix is representing an elevation value. This is a typical digital elevation model, but there different terms are also used like digital surface model, digital terrain model. There are some differences which we will also see in this particular lecture. So if we see a typical definition of digital elevation model is a 3D representation of terrain surface, and which is commonly for the planet. The planet can be Earth or Mars or a moon, which is a satellite of the Earth, or any asteroid as well. So for any natural surface we can create a terrain model. There are various techniques by which we can create these elevation models, which we will discuss in subsequent lectures. Also it can be defined that the DM is an ordered array of number that represent the spatial distribution of terrain attributes. Here terrain attributes means here that not only the elevation value, but some other values like slope values, aspect values, and other values can also be represented. This in a two-dimensional matrix, the cell value can also be some other value instead of digital elevation value. So for example, it can be a pH value of soil or a subsurface value, say groundwater surface, and so on and so forth. So it is not in a typical DEM or digital elevation model, we assume that the cell value is elevation, but otherwise for digital surface model, DSM or terrain model, we can have some other values as well. So this is the advantage of having such a data structure. So DM represents the spatial distribution of elevation above some arbitrary datum in a landscape. Generally, as we know that we use the data above mean sea level. So that can be represented, but even below mean sea level, the terrain surface can also be represented, but it is not that easy to create a below mean sea level terrain surface. DSM, as I have been just mentioning, the DSM or digital surface model is a surface which can also represent groundwater levels, which are the subsurface information, chemical quantities of soils and water can also be represented through DSM. So DSM, but the most popular term, as we will see very soon, is the digital elevation model, which encompasses almost every kind of surfaces which we deal in our due course or in our day-to-day practices. So the most common digital data of the shape of the Earth's surface is basically cell-based DM, because the data structure is simple and therefore a lot of applications have been developed on it, plus lot of digital elevation models, especially the free global digital elevation models at different spatial resolutions are also available. So DM is used as inputs to quantify the characteristics of the land surface, and DM is a raster representation, as I have already mentioned, of a continuous surface, usually referencing the surface of the earth. As you know that in GIS we have discussed that there are three main types of data structures which are handled in GIS. One is the vector data, but it is a discrete or discontinuous data. Another one data is the raster data, which is a continuous data. Our DEM or DSM or DTM all are the continuous data or raster data. And third model is TIN, which can also be used to represent surface using triangulated irregular network. So it's a irregular network of triangles can be used to represent a surface. So there are various types of models available to represent surface, but here in this particular course we will be more focusing on the raster structure, that is a typical a grid based structure, and that is the DEM. So surface, as we know, that are usually modeled with the raster data sets. A raster is matrix of cells, a two-dimensional matrix organized in rows and columns and covering part of the world. Or not only the earth, as I have mentioned, maybe like using satellite data, the digital elevation model of surface of moon as well as surface of Mars have also been prepared. So this is the technology which can be used to prepare surface models of any natural surfaces. Each cell in matrix represents a square unit of area. This is very important, that the unit of a digital elevation model or raster is always a square in shape. However, overall shape of raster can be either square or rectangular, but the unit has to be square in shape, and it contains a numeric value, that means the cell value, that is measurement or estimate for that location. So we can have a measurement about say elevation above mean sea level, or can have estimates, that means that through interpolations we can fill those cell values, and therefore the estimation is also possible using point data. So using point data through interpolations we can also create such surfaces or digital elevation models, which we will discuss when we will discuss how digital elevation models can be created. This is the typical example of a digital elevation model which we are seeing, and same model can also be represented in color. Very soon we will see. Here the values are represented, that means the high elevation values are having brighter tone, whereas the low elevation values are having a darker tone. Here the minimum value is 95 meter and the maximum value in this particular example is 3070 meter. And though we can assign different colors or shades to different values, but here we have used one scale which is continuous, and these two extreme values, that is the 95 and 3070 meter, have been scaled in between black and white. So they say two extreme members have been assigned these two colors, and rest of the values are in between, and therefore we are seeing a gray digital elevation model. Lot of features can also be seen while we see here a digital elevation model, but by doing some more processing the same model can be made more useful, and lot of information can be extracted using this. As I mentioned, that the same digital elevation model has been now represented on the right side in color, but instead of assigning black and white, you can assign a color palette, and there are different color palettes are available in different softwares, and then the entire thing is represented in color here also. Now one thing one has to remember always, what is important here is the cell value, and the way you are projecting using whichever the palette, the original values are not changed. The original value will remain intact whether you are representing in black and white mode or in shades of gray or in color or different color palettes. The original value of cells, that means elevation value in a digital elevation model, will remain same, except that while displaying on a screen or through projectors, you can change the colors. So, as I have already mentioned that DM is a raster grid data and it is a 2D matrix, though we can use and can use that Z value, that is the elevation value, and can create 3D also. So, some people call as a 2.5D, some people would like to call as a 3D, but unless we do not use, if we use that Z axis and give some vertical exaggeration, then only we will start seeing in 3D. So, those examples we will see also little later. As mentioned also that each unit, the cell, that is the cell is always square in shape. Overall shape of a grid or DM or raster can be either square or rectangular. So, these things have to be remembered. These are the fundamentals basically, and when we will go for further analysis and applications, these things will be utilized there. So, they are very important. So, DM can be represented as a raster 2D matrix grid of square cells, also known as height map when representing elevation, but as I have mentioned, it is not necessary all the time that we only use the elevation value. We can have values of certain concentrations of chemical quantities. We can have also the water table or any other value can be used to create a surface. Or as I have also mentioned that we can represent a surface using a different model, that is the tin, which is a some people call as vector based, or it is not truly a vector based model, but for a classification purpose okay, because it is not a typical raster. So, we can say it is a vector based tin model. Tin DM, that is means the DM or which has been created using tin, is also referred as a primary or measured DM, and whereas the raster DM is referred as a secondary or computed DM, because it is not directly created either through interpolations or using some remote sensing techniques and then further processing, and after that we create the digital elevation, a typical digital elevation model, and therefore it is called the secondary product or computed product. DM could also be acquired through techniques such as photogrammetry, using stereo pair data, LIDAR data, INSAR, that is SAR interferometry techniques we have discussed in the course of introduction to remote sensing, and land surveying by using typical topographic survey techniques. Various techniques are available, and latest ones based on the electronic theodolites or differential GPS can be employed to create digital elevation models. But the most popular one nowadays is based on remote sensing, that means either using photogrammetry techniques or INSAR techniques to create digital elevation models. Various models for the entire globe have been created at different spatial resolutions using remote sensing techniques. So, in subsequent lectures we will be discussing those as well. This is how a DM looks. When we zoom it and we want to read the values, then we can see here that these values, though there is a lines which are marked here, but in fact these lines are not there at all. It is just for our own understanding. The lines have been shown here for this matrix, but there is a cell of a square shape, and each cell will carry a value. That value might be an elevation value. Now, so we do not see this lines as I have mentioned. Instead, we use or see a layer symbolizing by a color ramp or maybe a gray scale, and spatial effects such as hill shading, which is a product or after processing of digital elevation model, can be created quite easily. We will see how it can be done, or may be used to simulate relief as in image, which is this is the example. So, the DM which you have seen earlier, one in the black and white or in shades of gray, one in the color, If we imply this hillside or shaded relief model, in short we call as SRM, then we can illuminate that surface, and therefore the same digital elevation model can be represented something like this. So now it is giving you much more depth perception as compared to the simple digital elevation model as shown earlier in black and white. Now, because both image, maybe remote sensing image or a digital photograph and a grid, both are raster, and some people get confused. Definitely both are raster, but there are some differences between a raster and means between an image and a grid. These are the things that both are raster models, and the shape of all raster data models can be either rectangular or square, and unit of raster or DM is always square in shape. This we have already discussed. Now, what are the differences? The major difference between an image and grid is it depends on the value, the cell value. So, in case of image, we call as the unit we call as a pixel, and a pixel is abbreviation which is picture element, because the value in a remote sensing image or in a digital image is not as the cell value in a grid or in a DM. So, that is why a different name is given for the that is picture element or pixel, and the value in terms of the what value it will carry. In case of image, it can be only positive integers values, whole numbers. Now, if it is a 8-bit image, then the values can be for individual cell can be between 0 to 255. But if it is less than that, then we will have less variations in the values, but if it is more than that, then we will have more variations in the values. But all cell values or pixel values in case of image will only be positive integer values. But the advantage with grid structure, though that is also raster, like for example digital elevation model, we call the cell as cell instead of pixel, and it can carry both positive and negative and integer and real values. So, all kinds of values a grid or a DEM can carry. What is the why it is required? Because if we are preparing a digital elevation model or handling a digital elevation model which is of a coastal area, now some values are above mean sea level, some values are going to be below mean sea level. Therefore, we require positive values as well as negative values as well. So, that is why the structure has been made in such a way that these positive and negative elevation values can be accommodated. Further, that we also require in a digital elevation model, not only the least count is say 1, we can have even 0.5, 0.25 and so on and so forth. That means instead of integer values, we also want to have real values of my requirement, maybe 1 place of decimal, maybe 2 as per the accuracy of models are there. So, therefore, grid cell values can be either both positive and negative integers as well as real numbers. These things have to be remembered because otherwise both are raster, but these two major differences are there. We call as a pixel instead of cell. In case of grid, we call as cell, and the values in case of image are only positive, whereas in case of grid, positive, negative, both integer and real values are possible. Examples are given here that on the left side it is a repeat example, all values here are positive, and this is representing, this is how it is represented in an image, whereas on the right side you are seeing the values are in real numbers. In this particular example, we do not have some values which are in negative, but they are not integers, they are all in real numbers, only up to 2 decimal places. But if it is required, we can have more precision in our data and can go for 3 or 4 decimal places. So, grid values, cell values can be either integer or real floating numbers. Now, there were 3 terms which were being used. Some people use interchangeably. Sometimes it is very difficult to even demarcate the boundary between DEM and DSM, but nonetheless we will try to see whatever the minute differences which exist between these 3 terms. Digital elevation model, DTM, that is the digital terrain model, and DSM. As you can see in this figure schematic, that this the digital surface is encompassing whatever is on the surface of, say for example, surface of the earth. That means the height of the house, height of the tree or bush, all are incorporated in the digital surface model. So, it is truly representing a digital surface model. Whereas, in case of digital elevation model, it is only minus all these objects, it is incorporating only the digital surface of the earth. So, this shows that what is the difference between digital surface model and digital elevation model. A DM, as you know, is a representation of the elevation of Earth's surface above certain datum, that is above mean sea level, in a digital form. It is achieved taking elevation measurement at regular, that is every, say for example 50 meter, depending on the spatial resolution requirement, or irregular space point, that is for every arc second, 3 arc second for example, over the Earth's surface. And there are various, as I have mentioned, acronyms used to describe digital elevation models, and 2 very popular ones are digital terrain model and digital surface model. So, these 2 terms are also there, like here one is this DM with the SRM, that is the shadow relief model we are having in the, so this is a typical DM represented in color. This is the same DM, here hill shading has been done, and therefore we are seeing better representation of the terrain. Otherwise, in the top example, it looks like a flat, except the different color values are telling some elevation. But here in the shaded relief model or in hillshade, things becomes very obvious. So, this is very good output of a DM. And these are the differences which one would observe in case of DTM and DSM. As I have mentioned, DSM represent the top surface of the earth. So, whatever the objects which are present, all that surface is included. In case of like LIDAR and other, when we employ these techniques to create the surfaces, we generally create a product which is called DSM. Whereas, for the maybe for the same area, DTM will look like this. So, this is, but generally what we the processing which we perform ultimately is on digital elevation model. So, there we use or assume a bare surface without humanly created objects or vegetation or any other thing. So, DEM are commonly built using data collected using remote sensing techniques, which has become very popular in recent years, and we will be seeing. Earlier we used to have land surveying techniques, maybe using like theodolites, or later on these EDMs or electronic distance measuring machines, or electronic theodolites, total stations, and now also we employ digital differential GPS or DGPS. A remote sensing technique is most popular, therefore it became possible to create even digital elevation model for almost all parts of the globe. And DM are often used, as I have mentioned in the beginning, in the GIS. We use extensively DM, drive various products or derivatives from DM, and then use these products along with some other data sets to create some new scenarios. So, that is in length we have discussed about how GIS works, how different things are there. But in this particular course, we will be more focusing mainly about the digital elevation model. And most common basis for this is a digitally produced relief maps, because this give you the feeling, DM will give you the feeling of a terrain surface, and therefore while employing this thing we can drive various products and plan things accordingly. While a DSM, that is digital surface model, may be useful for landscape modeling, city modeling, visualization applications, a DTM is often required for flood or drainage modeling, land use studies, many geological and other applications, there we employ these. Further, there are, as I have mentioned also, that there are no universal uses of term digital elevation model. Some people still call as digital terrain model and digital surface model, and you will find the usage of these terms, but the most common one in most of the cases people call as a digital elevation model. They would like to prefer to call as a digital elevation model. So, this digital surface model, as I have mentioned, that using LIDAR technique that creates the digital surface model, later on one can remove that surface over the earth surface and can create the digital elevation model. So, there are DTM represents the bare ground, and whereas DSM includes your whatever is present on the surface of the earth, and DM is also used as a generic term for DSM as well as for DTM. So, DM is a most common term which is used, and sometime instead of calling DSM, people just in simple terms it calls a DM. Basically one has to remember the structure, the values it carries, and how it has been created, because then it while using DM you will realize that these things will matter a lot while creating products from DM as well. So, other definitions also equalizes the term DM, DTM, define the DM as a subset of DM. Some people prefer like this, which also represents other morphological elements. There are also definitions which equalize the term DEM and DSM. It is also defined that DM is a regularly spaced grid and DTM is a three-dimensional model. But as I have said that if we use the Z value, that is the elevation value present in the DM, and you imply some vertical exaggeration, we too can create a 3D model. And the best example is like in Google Earth, the two main data sets are there. One is the satellite images acquired from various satellites, draped over a digital elevation model, and when we zoom it, we see in a 3D, because that the Z value or the elevation value is enhanced through this vertical exaggeration, and therefore we start seeing things in 3D. So, DEM can also be used to represent terrain in 3D as well. Most of the data providers, for example, USGS, ERS, DEC, CGIAR, Spot Image, ISRO of our own India, which is through NRSA, use the term DM as a generic term for DSM and DTM, because this is most popular term for all these terms. So, DM is the most popular, which encompasses this thing, but there are differences as we have already discussed. All data sets which are captured with satellites, airplanes and other flying platforms are originally DSM, because they encompasses the surface, vegetation, house or any other thing. But later on through processing we basically create DM. So, there are examples of like SRTM, which was a mission and a global digital elevation model for about 80% part of the globe was created, And other example is ester GDM, which has been created using photogrammetric techniques using stereo pair data. So different techniques, all are remote sensing techniques employed, and different digital elevation models have been created. Generally, the term DEM is used as a generic term as DSM and DTM. Now, as we can see further that DTM is a DM. Now, this is another way of explaining that a DTM is a DM that represents the elevation of the bare earth without taking into account any overground feature, that is tree or buildings, man-made. And whereas the DSM encompasses everything. So, DSM is a DM that represents the elevation of a surface or remote sensing will first meet when aerial photography is undertaking or top of a building, forest, etc. And thus, the resulting DSM includes the elevation of the bare earth plus the natural, that is the trees, shrubs and man-made features, for example building. So, an example of DSM is this SRTM, which was created, this SRTM DM was created implying the SAR interferometry technique, and which have covered about 80% of the earth, and at 3 arc second, that is 90 meter spacing, later on also 30 meter spacing, that means 30 meter spatial resolution DM from this SRTM mission has also been created for 80% of the globe. Only the polar regions were missing because of the orbital designs. This on the left, this figure we have already seen so that just to again recall that how DTM will look, how DSM will look, and in some countries DTM is actually synonymous with DM, and this means that DTM simply an elevation surface representing the bare earth reference to a vertical datum. And like in US or in other countries, a DTM has a slight different meaning, and DTM is a vector data set, which is not really true in that sense, because by definition all these are raster. So, different meaning will be there. The best term which we find is using DM. And now I will be doing some demonstration through softwares, how it looks our DM, how in black and white it looks, later on also you DM with the color, how we can change it without changing the original values, how a DM and SRM, that is shaded relief model or hillshade, can be combined together, and a new product very easily can be created. Also we will be discussing how when you zoom to the cell level, that is the unit level, how it will look, how we can read the values, and that will show us a unit of a DM, and also it will justify that overall shape of a DM can be either rectangular or square, whereas a cell level, that is unit level, is going to be always square. In this demonstration of GIS software, I am going to use a very popular software which is called ArcGIS. It has got 3 components: ArcMap and Arc Catalog and Arc Toolbar. But initially in this particular demonstration, I will be using only ArcMap, and will show the how DM looks, and when we zoom it and other things, then how we can see the details here. So when I add a DM file, digital elevation file, this is how it looks, and as you can see that overall shape here is rectangular. So we can have basically any shape of on the display, but in the background, because it's a 2-dimensional matrix, and therefore the overall shape of a DM or a raster has to be either rectangular or square. But suppose if the area is arbitrary, then how we will display, but the computer will store as a rectangular or a square, but the other areas which are falling out of our boundary will be assigned no data. And if we assigned no data values to the color of the screen, then we don't see or the background. So therefore we can see an arbitrary. But that demonstration will be done little later. But first here, that overall shape of a raster is always either rectangular or square, because it's a two-dimensional matrix. And if I zoom, then we can see even up to unit level. So if I zoom here and zoom further, now I can see individual cells of this grid. And you know that we have reached to the cell level, and therefore within a cell, the cell value will be always same here. So like here in this case, the value say coming 142 in this cell, wherever I will click, it will be always 142. But if I go here, then this is the next cell, and definitely a new value will appear. So another important thing is the shape of the cell, that is at unit level. In case of raster or in case of DM, it is always a square. So as mentioned in earlier also, that the overall shape of a raster or grid can be either rectangular or square, but unit of raster or DM will always be square. But in case of TIN, triangulated irregular network, the unit is triangle, and all triangles might have different shapes and sizes. So that thing we will be seeing much later. Now, as also mentioned, the DMs can be either displayed in the grayscales like here currently, or we can change the palette. So if we want to say display the same DM in a already available palettes, we can do it by applying this one. The important thing is that the cell values have not changed, except the palette has changed. So only instead of assigning colors between two extreme members, black and white, now here the colors have been assigned between say magenta to dark brown color. So this is one palette scheme. We can choose many. There are many palette schemes. Some are standard palette schemes are available for relief representation, because it's a DEM. This is that color scheme which is used for relief representations. So here, by some standards, we know that at certain level we get the snow fall and other things. So therefore, these areas have been shown as white, indicating that these are the very high grounds, and some lower grounds are there. At those levels, the vegetation is expected. Therefore, these are being displayed as green. But in nature, it may not be there, but in this DM model, we can have this one. So I am going to, as I showed to you, I can display in any of these color palettes, and there is not much problem. Now the same DM can be used to prepare a hillside like this one, and here the shadow of the slopes will also come, and that is why it is called hillside or shaded relief model. How these are generated, that we will be seeing in subsequent lectures. The important thing is here, by exploiting the capabilities of softwares, we can generate some beautiful products. Here this is black and white, this is having colors. So when I display one top of another, then I see only the top one. But if I go and change the transparency level here, like here in the display, I go for 50% transparent. The top layer, that is the simple DM, is now having 50% transparency. So what will happen? The hillside, which is just below, will also start seeing here, and this is what we see. So now we are having a shaded relief model with some beautiful colors. So just playing with the capabilities of software, different tools, we can really bring a lot of new things into our presentations. Important thing here is we are only doing all these changes which I have demonstrated here through this particular software is only at the visual level, at the screen level. The data, that is the digital elevation model or the product of digital elevation model, that is hillshade, will remain intact, no change in the values except in the colors. So that's the advantage of this thing, and this is achieved by a technology or concept which is called lookup table. So through lookup table, we keep changing these things. We can save also, but not as a separate file, but as a project. So project of, if I save as a project, the project will store the lookup table, but it will not create a new data set, and therefore it will not unnecessarily occupy your hard disk. So this care we have to take, that all the time we need not to save as a new file, but just will save the whatever we have performed, the processing which we have done, like in this case hill shading, and that too in color. So by taking this advantage, we can really develop lot of beautiful products for various uses, plotting and other things. So in this particular lecture, as we have discussed, basically what is DEM, how it is represented, what are the different terms used, and what are the differences between DEM, DSM and DTM, and at unit level, how cell values can vary, and so on so forth. Thank you very much.